properties heterostructures made on silicon, and then gallium nitride and gallium oxide. So gallium nitride, maybe many people just maybe not so much. So gallium nitride was discovered in Nagoya University, for which Nobel Prize was given. So gallium nitride is a wide band semiconductor. So it emits blue light. So it's very famous for blue light emission. But one of the most interesting properties, gallium nitride you can use for power devices. Power device means maybe many people know about power electronics. So I am relating many things to energy actually. So power electronics is nothing but like you can apply very high voltage. So you know about Schottky junction or like transistors. In this you can apply very high voltage and high current. You can operate in very high voltage and high current. That is called power device. So gallium nitride, then gallium oxide. So this type of materials also I'll discuss. Then I'll discuss about electrocatalytic properties of 2D materials. So in this case, it's come like fuel cell, metal air battery. Metal air battery, maybe many people knows about this and maybe new for someone. So metal air battery is that you use air as a fuel, and what you can do is that you can do oxygen reduction reaction at the same time oxygen evaluation reaction. So what happens with that, you can generate electron, and I'll discuss about it. So battery technology, one of the very important topic in the future to be going to be for electric vehicles or any other thing like that type of. Then I discuss about water splitting, which you can generate hydrogen. So hydrogen is one of the source of energy which you can store more large amount of energy. So I talk about water splitting cell, then about supercapacitors. So these are the things I am going to discuss about today. So first of all, so in present scenario, if you see the materials and device which are like energy conversion device, energy storage device, then other thing is sensor, one of the main important topic. Then bioelectronics. So all of our, so we know that the pandemic has created so much things. So bioelectronics is one of the has lots of aspects. So today I am going to talk about clean energy technologies in this talk. So if we see in this chart, we know about solar energy, then wind energy, hydro energy. So all this, if you can produce electricity, and you can transmit or say let's say for power plant. So then if you see the other like battery, fuel cell, all are integrated in mobile vehicle like cars or buses or trucks. Then all these are interlinked. Okay, so if you see that they produce nitrogen, CO2, H2O, you can convert to some other like ammonia or hydrogen, which is a large source of energy by electrocatalytic reactions. Then you can store in hydrogen. Then this hydrogen you can use for fuel cell car. So fuel cell car, Toyota is making it's called Mirai car, which is hydrogen-based fuel cell based car. So if you see from this chart, all are interlinked, and all are source for green energy technologies. Okay, you can convert to some chemicals or some like CO2. CO2 you can make some electrochemical reaction, and you can convert to some fuel. So this is a from this you can see that there are many aspects in green energy technology. So what we do generally in our lab is like we do lots of work on chemical vapor deposition. Chemical vapor deposition is like this CVD process. We can grow very high quality monolayer graphene. So monolayer graphene is like one atomic thick of carbon atom. So like it's like if you think about one carbon atom thick layer is around 0.34 nanometers of thickness. Okay, so you can see that it is the thinnest material you can synthesize. Then we do also liquid phase synthesis process. So by liquid phase synthesis process, what we do is we can oxidize graphite to graphene oxide. Then you can reduce it to form graphene, and you can get in a powder form or in a solution form. So these are two processes actually we use to synthesize various kind of material. Then we do device fabrications. I discussed in the very beginning that you can integrate graphene and silicon to make photovoltaic device or detectors, sensors. Okay, so I'll be discussing about these things. Then electrochemical reaction and electrochemical activity of these materials. So we do also we have done lots of electrochemical analysis of graphene oxide based material or nitrogen dope carbon materials or some of other materials. So first of all, graphene, as I discussed, graphene it's a one atomic thick sheet of carbon. So it's a sp2 hybridized carbon. So you have a localized pi electron, so which can move very fast in the sheet. That's why it gives very high carrier mobility, like move higher than 10,000 times higher than the silicon. So so graphene was discovered in 2004, for which in 2010 a Nobel Prize was awarded. And after that, lots of various kind of 2D materials actually discovered. So if you see, this is the Venn diagram of graphite. From the here you can see, you can get a Dirac cone. Okay, so in the Dirac cone, the conduction band and valence bands is connected, so you don't have any band gap, and it's a linear dispersed. From the solid state physics, if you see, it's a linearly dispersed band gap. Okay, so it's like it's a particular band structure for 2D material. So the electron can easily go from conduction valence band to conduction band without any because it has no band gap, right? So you have a very high electron mobility in graphene. Okay, so I hope many people heard about graphene. And then another interesting aspects in 2D material is that this is a electron dispersion of MOS2 in bulk. So if you see, in case of bulk, it has an indirect band gap. Okay, this is the highest position for valence band and conduction band. If you see, it's an indirect band gap, which is around 0.76 electron volt. Now, if you just take one thick means one atomic layer of MOS2, the band structure totally changes. So it's become a direct band gap semiconductor. So the highest position for conduction band and valence band, if you see, it's a direct band gap semiconductor with a band gap on 1.84 electron volt. So when you make 2D materials from bulk materials, its electronic properties as well as the optical properties or chemical properties significantly varies. So and so when you have this kind of optical direct band gap, you can do many things in this. Like it's very interesting for optoelectronic properties. Okay, so not only MOS2, then graphene, and then came hexagonal boron nitride. Hexagonal boron nitride is like it is same as of graphene. You can have same lattice constant for graphene, almost same lattice constant, around just 2% mismatch. So what if you replace these carbon atoms by one boron and one nitrogen atom all over here, then you can have a boron nitride, hexagonal boron nitride seed. But the hexagonal boron nitride, you don't have any free electron, or you don't have a sp2 pi electron. So by which it's an insulator. It's a very highly conducting. It's become an insulator with a band gap around 6 electron volt. So then there are chalcogenide, as I discussed about MOS2. Then there are many other things like magnetic material of yttrium sulfide, superconducting materials. So several other 2D material has been discovered. Okay, so another interesting. So these 2D materials has very interesting physics. So if you I just introduce you some of the interesting aspects of it. Then I'll go to energy related devices. So you can have like, if you have 2D materials like this, you can have biexciton. Okay, what is biexciton? So you can see about it. You can have a triexciton, combination of hole, electron, two holes and electron. Like if you see here, like so then interlayer exciton. It means in one layer itself you can have your excite. Okay, so then in intralayer exciton in individual monolayer. So there is lots of interesting physics in 2D materials. So please try to read about this. It's very interesting. Okay, so here I give some of the materials what we synthesize in our laboratory. Actually, I miss here maybe. So we use actually polymers like non-biodegradable polymers like polystyrene or polyethylene to synthesize graphene. So we can synthesize this type of hexagonal single crystal graphene, and this is a single layer graphene. Okay, so this type of single crystal graphene domain we can synthesize on catalytic layer. So this is synthesized on copper foil. Then there are lots of studies going on bilayer graphene, or like when you have a magic angle in between this, you can have lots of superconducting property, or like various you can have this type of Moire pattern in twisted bilayer graphene. So again, hexagonal boron nitride we synthesize from ammonia borane. So this is the precursor by which we can synthesize by CVD process, and we can get this type of triangular single crystal of HBN. Okay, so if you now, there are other studies going on heterostructures of this layer. So you can combine HBN layer, graphene layer, or like this is MOS2 layers to form a heterostructures of this layered material. So for chalcogenide, what we do is metal oxide or halide precursors combined with sulfur. We do CVD process to get this type of triangular or hexagonal single crystal of MOS2. So this is about a CVD process, what we synthesize single layer graphene crystal, HBN crystal, or MOS2 crystals. So this is the CVD process what we have done before, and this CVD process were not persist, and I have made this low pressure CVD or atmospheric pressure CVD on by myself, and we can control the layer numbers, and we have very good expertise on now in single layer monolayer graphene growth. So in atmospheric pressure, you know that it's very high pressure. So high pressure means it's significantly high, right? So in low pressure, what we go is like 40 to 100 Pascal only. And by this, we can what we can do is that we can control the flow of gas and interaction with the substrate. So when gas flows, this is called laminar flow, and in between this laminar flow of gas and the substrate, there is interaction with the substrate surface, and where nucleation of graphene or as well as HBN domain occurs, and it grows as a single layer on the surface. So depending on the metal catalyst, also you can have various growth mechanism. Like in nickel, you can have diffusion of carbon, then segregation of the surface. Where on copper, dehydration of the precursor, then nucleation and growth occurs. So, so depend on the pressure, depend on the catalyst, depend on the gas composition, depend on the precursor quantity. So these are the interesting aspect of a CVD process. So what I was talking that is like it depends on the catalyst also. What we do is that we purchase nickel foil from some company and in Japan. So these foils are really polycrystalline. So you don't have a particular crystal orientation. You can have like all kind of small grain. Then we annealed it in hydrogen in high temperature, and then we can make a single crystal copper foil. On a single crystal copper foil, the nucleation, so when you have a single crystal substrate, the nucleation of the domain of the graphene will be a same orientation. But if you have different grain of the substrate itself, the domain orientation of graphene domain orientation will be different, and that gives lots of defect in the grain boundaries. So we need it is always better to have a single crystalline substrate to grow high quality single layer graphene. So this is the like process. What we do is so this is the purchase copper foil. Then when we resolidify, you can see that how smooth it becomes. So you can FM study also shows very smooth surface we can obtain, and it's become single crystalline. Then in this kind of substrate, we can grow the graphene layer very uniformly with having less defect, and the so 2D I2 2D is like the graphene recognizing peak at 2000. This is a Raman analysis actually. So 2D peaks come around 2700 around. Okay, the 2700, and the graphitic peak is around 1600. So all in Raman spectra, you will be always seeing that 2D peak is more than twice of the G peak for a monolayer graphene. Okay, and this is just defect peak, D peak. So we can see that it's uniform throughout the measured Raman spectra of the graphene synthesized on resolidified copper foil. So we can get very highly uniform monolayer graphene on resolidified copper foil. So if you see, this is a transfer monolayer graphene on silicon oxide. So it's monolayer graphene, and we can now grow this monolayer graphene in wafer scale. So actually this is, we grow first on copper foil, resolidified copper foil, then the monolayer graphene is transferred to, this is transferred to silicon oxide. This is a silicon oxide wafer. This is a 4-inch wafer. So we can transfer by chemically etching the copper foil. Of course, we give a polymer support on the graphene first, then we etch the copper foil, then we transfer to the silicon wafer or any other arbitrary substrate. We can transfer the graphene. Okay, so this is some of the thing of nucleation of growth I would like to discuss. In this study, what I previously was talking, that when you have a polycrystalline, your domain orientation are significantly different, because the copper, let's say you have 111, 110, various orientation. So what will happen, let's say this domain and this domain having almost similar orientation, but this domain has different orientation. Okay, so edge orientation is different. So these are the hexagonal crystals with different edge orientation. Then we get some kind of hexagonal or round shape, not perfectly hexagon, not perfectly round shape. Then in another growth process, what we get is that completely round shape. So this, when you have a completely round shape, it is an isotropic growth model of the graphene domain. And when you have a hexagonal domain, you have an anisotropic. Okay, edges are defined. Here, edges are not defined. It's a round shape. So why this type of growth happens in our CVD process? So what we see is that when you have high amount of gas flow with the precursor, say here argon is 100 SCCM and hydrogen is 2 SCCM. When you have high amount of gas flow, the precursors flows very fast on the surface substrate. So interaction time of the substrate surface and the precursor is less. So in this case, we get hexagonal shape. But when you half the amount of gas. So this time the precursor is moving very slower than this. So you have much higher interaction time of the precursor and the substrate. So more precursor on the substrate. So you can have a round shape growth of the crystal, isotropic. So here we show that controlling the gas amount of gas putting in the CVD process, we can control the amount of precursor flowing on the substrate surface, and by that we can tune the isotropic or anisotropic growth. So in both cases, if we see the Raman peak of the crystals, it's a monolayer crystals, and good quality for both the cases. So once again, if you see in anisotropic, we have a small hexagonal crystals. This is just 5 micron scale, but in same growth time, we can have a very large graphene crystal on the copper substrate. Okay, so this was what I discussed, some interesting aspect of graphene growth by CPD. Okay, then I was talking about that HBN. HBN is nothing but like you can replace all the carbon atom by boron and nitrogen alternatively, and you can have a hexagonal boron nitride sheet. So just like you have in graphene, you can have a delocalized electron and band gap is 0. But in sp2 the BN, it's a polar BN bonds and do not give delocalized electron. So band gap is very high, 6 electron volt. Okay, so and lattice mismatch is very less, so it's quite interesting. So many people they do that graphene, although it has very high mobility, so when you make devices, you have to put on some insulating substrate. Like, so people use silicon oxide, but silicon oxide, you have lots of dangling bond, due to which the carrier mobility reduced significantly. So people use nowadays HBN. HBN is insulating, high band gap. So, but because it's a 2D layers and you don't have any dangling bond, so you can have very high mobility of graphene on HBN. So it's an interesting aspects. Then the CVD process of HBN growth by ammonia borane. So in this case, ammonia borane is like is a borazine. Borazine is like you can have a hexagonal ring of nitrogen and boron, and you can utilize this borazine to break down to grow these hexagonal boron nitride triangular crystals. So you can have individual crystal growth like this on copper surface. This also we grow on copper foil. So surface, then you can, these crystals merge together to have a continuous film. So these are the HBN here, and these red part are oxidized copper. So these are vacant position, but almost is combining each other to form a continuous film. Okay, so you can have a triangular crystals, then this is a continuous film of merged triangular crystals. But interesting aspects, and if you see one triangular crystal is like that, the another is like that, opposite oriented. So the edge of the two triangular crystal is oppositely oriented. So why this type of happens, if you see from reviews papers, so when you have nucleation of these crystals, so if the growth of the crystal start from boron atom, you can have like a nitrogen atom. So you can have this type of oppositely oriented triangular crystals of HBN. So it's very interesting aspects of HBN growth on by CVD process. Then what we can do is that same like graphene growth, we can control the edge structure. Okay, so by manipulating the growth process, we can grow this type of perfect hexagon crystals, or this type of truncated triangular crystals, or this type of imperfect round or hexagonal structures. So in this case, what will happen is like that. Let's say this is a perfect triangular crystals. Let's say all atoms, outside atom will be nitrogen terminated. But if you have this type of crystals, you can have boron or nitrogen atom terminated crystals. So you can have some edge effect on these crystals, because it will be not terminated by a particular atom. It will have both the atoms. So it can give some other electronic or chemical properties to these crystals. Then about MOS2 growth or chalcogenide growth. So in case of chalcogenide, as I discussed before, when you have a monolayer of MOS2, so MOS2 means you have a one molybdenum atom in the middle. In the top and bottom, you can have two sulfur atoms. So it forms MOS2 layers. And in case of MOS2 layers growth process, we use like MOA3 or for WS2 growth, WO3 or chloride. We use very nice crystals. We can grow like these triangular crystals, truncated crystals, or hexagonal crystals. Okay, so we can grow a very nice continuous film. So this is a MOS2 layers on silicon oxide, and the same SEM image or so you can have, because it's a single layer and have a direct band gap, you can get very good PL, photoluminescence, from a single layer. But if you have a bulk, MOS2 will not get any kind of PL. So by growing a monolayer and the quality of the single layer MOS2, you can evaluate by the photoluminescence properties. Okay, so I discussed about the CVD process, how to grow graphene, HB, and MOS2, right? So I'd like to discuss how we can integrate this to form some devices. So what we do is that we combine graphene, MOS2 with other conventional semiconductor like silicon or gallium nitride. If we see from the metal, or all of you have like many people like solid state physics from knows that density of state. So by density of state, you know the electron. So in metal, you can have this type of density of, when in Fermi energy there is lots of electron. So electron cannot move easily. So this is like means it's lots of electron at the Fermi energy. Okay, this type of density of state for metal. But for insulator, you have lots of very high band gap. Okay, this is valence band or conduction band. Then semiconductor, and depending on the doping, you can have a dopant band, right? This type of density of state. But in case of graphene, as I discussed, due to linear dispersion, you can have a zero band gap, and at the Fermi energy, where the Fermi energy, there is no electron at all. There is no zero electron. But in case of metal, you have highest number of lots of electron. Okay, so it's totally different for the graphene and metals. In graphene, you have no electron at the Fermi energy. Of course, if the graphene is doped like p-type or n-type, then the Fermi energy will be shifting. Okay, so that is a interesting prospect, that how this type of graphene, if we integrate with silicon, what will happen. So we can make some photovoltaic devices, like if we deposit graphene on N silicon and make a photovoltaic device, and it form a Schottky junction, and this type of Schottky junction now maybe 2 to 5% efficiency you can achieve. Maybe there are some papers which theoretical analysis shows that you can achieve around 30% of efficiency in this type of solar cell. Then we integrate graphene with gallium nitride. So I discussed about graphene, so we know that it has very high electron mobility. And gallium nitride also I said it has a wide band gap semiconductor. It is a wide band gap semiconductor of 3.4 electron volt. Carrier mobility is around 2000, little bit higher than silicon, or almost similar to silicon maybe. Then critical field. This is the important aspects. The critical field is very, very high. When one material is critical field is very high, you can apply very high voltage. Like in a small Schottky diode, you can apply thousands of volt, and you can make that switching devices, or this called power devices, power electronics. So when you have electric car or any kind of electric devices, this type of power this type of power devices are used. So what we have studies is, okay, so this is what I talk about power. So because this also integrate related to somehow to the energy field, so we can have high voltage operating devices. So like you can have silicon carbide. Silicon carbide has like this type of band gap. Then gallium nitride, okay, high voltage operation, high frequency operation, high temperature operation. So there is another new semiconductor is emerging, is like gallium oxide. So gallium oxide is much easier to synthesize than gallium nitride, and it has a higher band gap. So and it has much higher critical field than any other material. Like is like much higher than silicon carbide and gallium nitride. So this is one of the emerging semiconductor for power electronics device. And okay, so this we do graphene and then gallium nitride and gun Schottky junction fabrication, and it's shows a Schottky junction behavior. And when we irradiate UV light, because it has a high band gap, right? So when you illuminated by light below 400 nanometer, then you can get a photovoltaic action in this type of device. So what we can do is that we can make this type of device self-powered UV sensors. So we can use as a sensor device. So we did some temperature dependent characteristic in with temperature, how the electrical characteristic senses in graphene gallium nitride, and so it shows that barrier height, modulation of barrier height in graphene gallium nitride junctions. So then okay, what is the time now? Okay, so maybe I am discussing lots of stuff, so I skip some of things. Then this is graphene gallium nitride gallium oxide heterojunction. So we can make graphene and gallium oxide heterojunction similar to graphene gallium nitride. So in this case also, what we do is that see the photoresponse properties. So when we because it has a band gap of 4.8 electron volt, so we illuminate it with around 254 nanometer UV light. So it comes in deep UV beyond the solar solar, it's become a solar blind. So we can get photovoltaic action in this case also, graphene gallium oxide, in a solar blind region, solar blind deep UV region. So we can use this also as self-powered UV sensors. Okay, so it's very interesting prospect. Okay, so this is the what we did beta gallium oxide. Then we use another wide bandgap semiconductor like copper iodide, and we get very nice photovoltaic action in deep UV. Okay, so this is not in solar. It's not a solar cell. It's become a deep UV photoresponsive device, which shows photovoltaic action and very good diode characteristics. Okay, then okay, I skip this one. Okay, then I'd like to discuss about materials for catalytic application. In this, what we did is like we did lots of stuff of oxygen reduction reaction, then hydrogen evaluation reaction, and oxygen evaluation reaction. Of course, there's this catalyst can be used for like CO2 reduction reaction as well. So okay, first of all, what we in this case we graphene. So when you graphite, you oxidize, you can make graphene oxide, and you can dope by various heteroatoms like nitrogen, sulfur, or boron, and you can make them catalytically active. So we make we measure various electrochemical analysis in this type of cell, and this is a CV analysis of some materials. So in this case, what is coming is like fuel cell technology. Okay, so in fuel cell or oxidation reduction reaction is very important. Then metal air batteries. Metal air battery, you have a electrode of metals like lithium or zinc or something like that, and the other side, this side you have a porous electrode which you have a bifunctional catalyst. Like in this electrode, you have oxygen evolution reaction as well as oxygen reduction reaction. Both happens. Okay, so then the OH ion will go this side, then electron will flow like this. So it's a metal air battery is very interesting because you are just using air, and you can do this in water-based electrolyte like KH 0.1 molar or something like KH solution. So it has a high power density than the lithium-ion batteries also. So it's a very interesting technology. And water splitting technology cells are what you can do is like electrocatalytic and photocatalytic. So what we studies here most is electrocatalytic. So in one electrode there will be oxygen evolution reaction, another hydrogen evolution reaction. So hydrogen evolution reaction, by this, if you can generate hydrogen, and storing energy in hydrogen is one of the most important aspects what I talk about in the very initial beginning of the presentation. Then supercapacitors. So capacitors is also very important device for many applications. So the difference in battery and supercapacitor is that capacitor you can have very high energy density, but it's for very small time operation. But you can have a low power density, but you can run it longer. Okay, so so you can have supercapacitor like EDLC based or pseudo capacitor, redox supercapacitor. So what we are looking for the ORR, OER, HCR catalytic reaction is like develop alternative catalyst to platinum group noble metals. Then in this type of catalyst, we are looking for low onset potential of reaction, reduced over potential, high current density, and long-term stability. Okay, so for this we synthesize graphene oxide by our modified methods. So we can produce in very high quantity. So we especially used some techniques in this synthesis, and this is a solution of graphene oxide. And when you oxidize graphite, so the layer distance between the graphene layer increase and 1 nanometer around in the oxide layers. So when you measure the XRD, you can basically graphite. There is its XRD peaks around 25 to 26 to theta, but when you oxidize it, the 2 theta peaks, you can get a strong peak around 10 to 11. So this corresponds to the graphene oxide. Okay, so again, when you reduce it, so this we reduce by annealing. So reduce means you remove the oxygen, most of the oxygen. Then these peaks again gone down, and you have just like small graphite related peak here. So then what we did is that we combined this with cobalt oxide, and the cobalt oxide also cobalt oxide can be two different forms. This is COO. There are CO3O4 also, but we got the COO phase with the graphene oxide. So we combine it metal oxide. Metal oxide combination is important because it can boost your reactivity, or you can get a redox supercapacitor. So we tried this type of things. So this is a graphene oxide layers. So you can see the layer structure very easily. Then this is like nanoparticles, cobalt oxide nanoparticles in this sample. So we can see the C101 peak, but I may have not included the cobalt oxide peak. So we see the reactivity of this sample. So this is a CV analysis. So when you have CV analysis, you can see very clear OER. This is in this measurement are done for silver chloride electrode, and we are making it RHC scale. Okay, so in RHC scale, if you see, this is around the reaction start onset potential around 1.7. This is for the cobalt oxide geo sample. Then this is ORR sample. Means you have both OER and ORR. So it's you have a bifunctional activity, so it can be used for metal layer batteries. But for this is RGO, which is reduced graphene oxide. Here the ORR activity is good, but this OER activity is not good. So with metal incorporation, we have much better OER activity. Okay, so if that is CV, so we have LSV, linear strip voltammetry graph. So if you see here that this is the onset potential for the cobalt oxide GO and very good OER than the RGO and GO. So this is quite interesting for us. Then if you see the ORR, oxidant reduction reaction for the graphene oxide and cobalt, graphene oxide is quite less, but for RGO and cobalt oxide, graphene oxide, almost the onset potential is coming around 0.8. This is also in RHC scale. Okay, so this is almost same for RGO, and both sample has almost similar ORR activity. Then same material, or we do it for the GO and RGO. We study the capacitance measurement, and you can measure the specific capacitance as well as electric double layer capacitance by sensing the scan rate for the CV. So we measured from 25 to 500 millivolt per second scan rate, and in this scan rate, you can scan rate per. So in the middle, if you see these differences of current is delta I. So if you plot this versus scan rate, and you can find out the electric double layer capacitance using these equations. Okay, this is not so high at present. For RGO, we have around this much of, so GO, we get much higher double layer capacitance. Okay, so then we can make the specific capacitance by plotting from we can calculate it from the previous equations, and we can see that specific capacitance around more than 80 farad per gram for the GO sample, graphene oxide sample. So these are like you can, of course, we need to enhance much more of the capacitance, but we show that this type of graphene oxide and solution-based synthesis materials can have very good capacitance, and we can develop some supercapacitor based on this material. Then I come in, like, we synthesize metal incorporated nitrogen dope CNF. So in this case, we use melamine, and we grow some interesting structures. These are very highly dense and randomly oriented graphene-like structure. Then you have metal incorporation in this, and we synthesize this in bimetallic, nickel chromium foil. So it's two different metals. So it helps to grow this type of structures. So when we see, like, you can have nickel and chromium incorporation, then we have nitrogen incorporation in the fibers. So if you see graphene, nitrogen can incorporated in different form. So if nitrogen atoms replace one of the carbon atom in this type of ring, it is called graphitic nitrogen. So if it is replaced in the this type of outer, so this nitrogen is connected to all edges to 3 different carbon. So it is graphitic. But in case of if it's this type of connection and it has in a hexagon, but it is no third bond with the carbon, then it is called pyridinic. Then another, if you have a 5 ring, 5 atom ring, and there is a nitrogen atom, it is called pyrrolic. So all these 3 nitrogen in a graphene sheet has different activity, and it has been shown that pyridinic nitrogen can have very high catalytic properties. So this type of material we also tested in 0.1 molar QH solution. So this is 0.1 molar QH solution in water. Then we do the CV analysis in nitrogen saturation condition and oxygen saturation condition. So if you see that if you have oxygen saturation, so we can have very good ORR activity, like oxygen reduction reaction. Same, we do a much CV analysis in a wider voltage range from 1 to -1 volt. So if we see, this is the ORR, and here is this like OER activity. So it's bifunctional activity. Then there is 2 other peak. So if you have learned electrochemistry or studied about this, so if you have a oxidation, when this is the oxidation of the metal, so we have a nickel chromium, so you can see that there is a oxidation of nickel here. Then when you come back, this is a reduction. So I have not, maybe who have not studied the so this is a Faradic region where you have chemical activity, but when there is a no chemical activity, this is the non-Faradic region. So these all are measured in the capacitance measurement are done in the non-Faradic region of the material. So okay, so that so this is a Faradic current, and this is a non-Faradic region where we can measure the capacitance of the material. Okay, then so this is a CV analysis. Then this is a linear sweep voltammetry. So we have just one sweep. So this is the OER and this is ORR. So this is all measured in 0.1 molar QH. Then this is OER, then HCR. HCR means you have some hydrogen evolution reaction as well. Okay, but whoever doing research in electrochemistry on this kind of some electrochemistry, then they knows that HCR reaction is much more sluggish in alkali solution. Then this is the we do some RD, rotating disk electrode analysis. This is also linear sweep. Okay, this is just for the electrode where we put our catalyst. So for the electrode, not so much activity. When you put the material, it has very good ORR activity. Then this is a Tefel plot from which we can measure the over potential of the reaction. Then this is the RD rotating this electrode measurement. We have measured in 400, 800 and different rotating speed, and we can make see the how much electron. So this ORR reaction is 2 electron reaction, or it can be 4 electron reaction. For like say for fuel cell we need a 4 electron reaction when in which make your OH ions. But in case of like 2 electron, peroxide generation is much occurs. So that is not suitable for fuel cell, or of course peroxide generation also interesting topic, but not for fuel cell or metal air batteries. Okay, so this is another we use different metal alloy, and we get very good CNF structure with metal incorporation. And if we see, these are the CV analysis. How much time I can have more? Hello?
10 more minutes.
10 more minutes, okay. So this is the electrochemical analysis of the metal carbon nanostructures. So again, we did this for a wide wavelength, wide potential range. So this all are still in silver chloride reference electrode. So this is OER is going on. So here is the your ORR activity. So if we see only the ORR, so this is for oxygen saturation in the solution. So if we put oxygen gas, you can have much better ORR activity. So and this is for the only the OER. This is a CV. So we then compare with this with platinum, which is the standard catalyst for fuel cell or ORR reaction. So we can see this is for platinum, this is for our catalyst, and we can have around 200 to 300 millivolt difference. So which is not significantly. So our catalyst also is quite promising with low over potential as well. Again, we do the RD measurement, and in case of this catalyst, we can get around 3.6, like 4 electron reaction. Okay, then what we do is like we study this OER reaction. So in OER, what we see is that iridium oxide, one of the so iridium is a noble metal, so it is one of the best OER catalyst. So we get much better than the commercially available iridium oxide. So this is commercially available iridium oxide, and our catalyst is much better than onset potential as in terms of onset potential and in terms of current density as well. So we are expecting very good in this direction. We can have maybe much better catalyst. Okay, then I discussed some like MO. So I did this discuss about MO synthesis by CVD process. So what we can do is that we can do some solution process by hydrothermal synthesis process. So in this hydrothermal synthesis process, we use ammonia trimolybdenate and react with a reducing agent like urea and do the hydrothermal process. And what happened is that if we do this type of hydrothermal process, we get a mixtures of MOX and MOS. So when you do have oxide and sulfide, in between themselves can make heterostructures, and it can give very good catalytic properties. So we can see that from XPS analysis also that we can have some MOX and MOX and some sulfide-like structures. So we did the HCR analysis for this material synthesized by the hydrothermal process, and the hydrothermal process shows that really hard. So this is the sample, and sample after 50 cycles. So the catalytic activity reduced. Sample means the MOX and MOS2 related structures. But what we did that the same materials again we combined with graphene oxide, and after 50 cycles it has the HCR reaction has improved. Very high current density we get, and as well as the onset potential is also around. This is in RHC scale around 0.2. So maybe the for platinum will come around 0 around this month. So around 200 millivolt or that much of difference. But with combining with GO, the stability increased, reactivity increased, and it shows very interesting for us. And this type of catalyst can be ideal to replace platinum for hydrogen generation. Okay, this is the conclusion of my talk. So I discussed about CVD process to synthesize graphene, HBN, and methyl disulfonide. CVD process is very interesting because you can grow very nice monolayer graphene or HBN or methyl disulfonide on substrate, or you can grow as if uniform film, not by solution process. Maybe to grow monolayer uniform film is very difficult by solution process. But solution process also has advantage, as I discussed. Then graphene layer were directly integrated and transferred on silicon gallium nitride substrate to fabricate photovoltaic device, and you will based sensor device. Then okay, discuss about sorry, there is some spelling mistake. Graphene, integrated gallium oxide, and gallium nitride, and ultraviolet photoresponse device. As I mentioned, gallium nitride and gallium oxide are the most important wide bandgap semiconductor for power electronics devices. And then discuss about fuel cell metal air batteries. So batteries technologies are the most importantly studied at present because of the EV electric vehicles, and then of course hydrogen energy, then fuel cell, all are very important devices going to be in the coming decades or to achieve the carbon neutral. Then I discuss about graphene oxide based material and their electrochemical reactivity and their importance. Then we synthesize some metal incorporated carbon nanofibers, which shows tri-functionality like ORR, OER, HCR. All three reaction we can observe in this kind of catalyst. Then I showed some MOX and molybdenum oxide or sulfide heterostructures like the material synthesized by hydrothermal process, which shows excellent hydrogen evolution reaction with low onset potential and excellent current density. Thank you very much. So I'd like to thank Professor Tanimura from NIT and